So now that you're comfortable with applying and transforming the spring mass damper into both state space representation based on the last activity, as well as the transfer function approach that we took in last class, now let's take a look at a higher order differential equation, single differential equation that's higher order, and apply both of these techniques to this particular differential equation. What this is going to show you is that the same techniques can just be applied on a kind of like a larger scale, and I hope that this kind of longer, larger, higher order differential equation helps you see some of the patterns that are involved in both of these representations. So take a moment, take a few moments, and go ahead and work out both the state space representation and the transfer function representation for this particular system, given that the input is u and the output is y. So transfer function means that you'll be solving for capital Y of S in terms of U of S. And the state space representations means that you're going to be forming ABC matrices where the output Y is indeed your output. So take a few moments, solve that out, and then we'll go through my solution. So this has a lot to it. The solution has a lot to it. So this is my answer for both parts, just if you wanted to check both of them right now. So up here is our state space representation, and down here is our transfer function representation. So one thing just to mention here as we look at this is the fact that we have a fourth order differential equation. And again, this is what's hopefully going to become more and more clear as we do more examples. But the order of that differential equation, I have one differential equation and it's order 4. And that is why this ends up being a vector valued differential equation that has 4 states in it. And it's also why the highest power in the denominator of this transfer function is 4. So that 4, all those 4s are all related and important to be related. So now let's take a look at the two different solutions, starting with state space. So in the state space approach, what we do is we take the easiest thing to do, again, there are many choices, but the easiest thing to do is to take our unknown y of t and set that to be our first variable. Then, because we're going to need variables that represent all the way up to capture that y quadruple dot, we need to start taking derivatives. And so we're going to define a new variable as being y dot. So that's x2. We're going to do that again for x3, and that's y double dot. And then we'll do it one more time for x4, and that's y triple dot. And again, because of the pattern that we keep using, we stop here knowing that we're going to be taking derivatives of x4, x3, x2, and x1. And when we take a derivative of x4, we're going to get x4 dot will be y quadruple dot. And that's what brings us back to this equation. And so it's that reason why we stop here at only x4 and we don't define x5 is equal to y quadruple dot, because we don't know the derivative of that is y to the 5th derivative, and we don't have any information about that. So we stop here, but again, the easier thing to do is just remember that if you have 4 up here, 4 derivatives, that's the highest order, then you're only going to need 4 states to represent that. So again, the magic in the state space representation is that I take the derivative of x1, and I take the derivative of its definition, so that's y. I take the derivative of y, that's y dot. And that happens to be exactly what x2 is defined to be. So I get that x1 dot is equal to x2. And so this same pattern happens over and over again until you get down to your last derivative. So when I do x2 dot, that's y double dot, and that's exactly what we defined as x3. Then I take x3 dot, that's y triple dot, and that's exactly what I defined to be x4. And then finally, like I said before, we're going to take the derivative of our last state, x4, that's x4 dot, that's y quadruple dot, and that's when we don't have any more information from this line, so instead we come back up to the first line. And that allows us to rewrite this whole differential equation in terms of y quadruple dot. And that just gives me the fact that I get this expression that includes the input u, y dot, y double dot, and y triple dot. And here, this is the fact that I'm able to write y triple dot in terms of x4. So I plot x4 in there. Y double dot in terms of x3. So that's x3. Y dot in terms of x2. That gives me x2. And y in terms of x1. And that gives me x1. And then I keep u as my input. And so now I just need to aggregate all of this together. And again, it may be useful to you to write this first in its vector form without trying to make it in matrix form. So that would mean that you write all four of these states, their derivatives, and you're just going to write that out in terms of, so x1 dot, we wrote that to be x2. x2 dot, we said that was x3. x3 dot, that was x4. And now x4 dot, that's the interesting one, we get this minus 3. Actually, let's go ahead and write that a little bit differently. So let's instead change the order so that it's a little bit more suggestive. Let's say that is going to be minus x1 minus 7x2 minus 2x3 minus 3x4 plus u. And so now this is our set of related differential equations. They're all first order, but they're coupled because now they're all kind of each line could have any of the x's involved in it. So to change that now into matrix form, we're going to fill this out. And again, this really just comes from insight and practice, knowing that this column is everything to do with this variable. So when I take this vector x and I multiply it by the A matrix, this x1 multiplies everything that's in this column. This x2 multiplies everything in this column. This x3 multiplies everything in this column, and this x4 multiplies everything in this column. So these columns kind of belong to these different terms, and that's what makes it super easy, is we know that here we have an x2, so that's why I put a 1 in front of in this element, because it's the x2 element, and the coefficient here is just 1. Similarly, this is 1, and this is 1, and so that's why I put 1s here and here. And then now I've rewritten this kind of in this order, this increasing order, and so that's why I have a minus 1, minus 7, minus 2, minus 3, because I have minus 1, minus 7, minus 2, minus 3. And then I add another term, because that's the input term. And then finally, I just have to express what our unknown is, y, in terms of our new states, x. And the way that we define them, that makes that very easy. It's simply just the first one. And so this is how we derive the state space representation of this fourth order differential equation. When we go to look at the transfer function approach, now what we're doing is we're relying on the Laplace transform. So again, we're taking the Laplace transform of both sides. Because this is a very long equation, I'm going to go ahead and write each of these particular terms as a different line. And then I'm going to take the Laplace transform of u, and that gives me capital U of s. I've dropped the s dependence on y simply because we've got a lot of things going on here. So for each of these, so for the fourth order, I get a s to the fourth, and then descending powers in the initial conditions. Then I need to make sure I keep this coefficient. So that coefficient needs to stick around, and that multiplies all of the terms inside. That's a super common mistake I see on homework and exams. So make sure that you keep that coefficient around and then substitute in the Laplace transform of y triple dot, and that gives me this third power of s and descending powers of initial conditions. I do that similarly for the second order derivative, so I get that coefficient, and then this is the Laplace transform of y double dot. This is the coefficient 7 and the Laplace transform of y dot, and then y is simply the Laplace transform of little y of t. So that's also a common mistake. So make sure that when you take the Laplace transform of y of t, you make sure that you write down a capital Y of s. For some reason that becomes confusing for many people. So in this case, we're interested just in the transfer function between the input and the output, and so we're not going to take initial conditions into account, and that simplifies things greatly. So everything goes away except for these capital Y terms. So we just keep all those with their coefficients, and that gives us this. And it's no coincidence that if you look at the coefficients, 1, 3, 2, 7, 1, they match the original differential equation, 1, 3, 2, 7, 1. And so you're going to see that, and that's a pattern that's going to happen again and again simply because of the way in which we do the Laplace transform. So it's super easy, if you know that you have 0 initial conditions, to go directly from this single differential equation to its Laplace transform version. And so that means that when we solve for y, that's going to give us now capital Y of s in terms of 1 over s to the 4th plus 3s cubed plus 2s2 plus 7s plus 1, and that's multiplied by capital U of s. And again, this denominator comes directly from this differential equation, so it's very easy to go from one to the other once you get used to how it all works.